In today's video, we're going to be talking about cyclic alkanes. So the naming of cyclic alkanes is actually quite simple. All you have to do is you take the linear name based on the number of carbons and add the word cyclo to it. So if you had a four-membered ring, so that'd be a butane, you could simply call this cyclobutane. And now when we're looking at naming, we also have to think about when we attach something to that ring, how do we talk about its orientation with respect to other groups? So in this case, when both of these groups, in this case methyl groups, are on the same side of the molecule, we call this cis. When they're on opposite sides, one coming at us and one going away from us, we call this trans. So again, cis is when groups are on the same face of a molecule, and trans is when groups are on opposite faces of the molecule. So one way of remembering this is when you're thinking about the Trans-Siberian Railroad or something like that, you're going across all of Siberia. And so now if we were to, we can use this type of nomenclature to describe the different orientations of these groups on this now 5-membered ring. So it's a pentane-based or a cyclopentane. You could say that this blue dot and this blue square are cis to each other. The blue dot and the red dot are trans to each other. The red dot and the blue square are trans to each other, as is the red dot and the red square. They're trans to each other. And these are cis to each other. So this, and this are all cis to each other. And they are trans to that red dot. Let's look at ring sizes and the strain associated with this. So the smallest ring is a 3-membered ring, so it will be a propane-based name, cyclopropane. And cyclopropane is actually quite strained. You know, if you looked at a 3-membered ring, or a triangle, as we sometimes call it in geometry, there's a 60-degree angle in a triangle. That's an idealized triangle. So the problem is that 60 degrees does not equal 109 degrees, which is the idealized angle for an sp3 carbon. If you notice, all of these carbon atoms are sp3 hybridized. So the molecule has to distort, and when it distorts, that creates a tremendous amount of strain energy. It's highly strained. Now, if we look at butane, or cyclobutane rather, because it's a 4-membered ring, there's a 90-degree angle in there, and it's still actually highly strained. It's still not 109 degrees, so it's still a very highly strained molecule. If we go one carbon larger to the cyclopentane, now that angle, that interior angle, is about 108 degrees, which is pretty good. It's almost exactly the same as the idealized angle for an sp3 carbon. Now I will point out that this particular molecule is not flat. We'll look at that in another few slides. Now we look at this 6-membered ring, cyclohexane. So if you were to look at the geometric math of this, it would say that the interior angle should be 120 degrees, which is too high now. It's much bigger than that 109 degrees. But the key thing to think about is that's true if the molecule is flat. And spoiler alert, it is not flat. And so, as it turns out, neither is that cyclobutane is also not flat. It actually sits in this kind of puckered shape. And cyclopentane is also not flat. It actually sits in more of an envelope type of orientation. The thing that's amazing about cyclohexane, which makes it kind of the Lord of the Rings, is that it has 0 strain energy. And we're going to look at why that's the case in the next couple of slides, or in the next slide. So the reason that cyclohexane has no strain is that it sits in a conformation called a chair conformation. And I've made a model for you here. And we're going to be looking at this model in the side video as well. So the key thing to look at for the chair is that it's a bunch of perfectly staggered Newman projections. It's really quite remarkable. All of them are in this in the ideal sp3 angles. So every single angle is perfect. And if you walk yourself around this chair, like I'm doing here, every single bond you look down has this perfect Newman projection. It's really, again, quite remarkable. So now we have to look at how we can draw our chairs. And so the best way that I know how to draw a chair is you start off with a series of parallel lines. The first set of parallel lines, I always like to think about this as a set of lines that if you were to drop a drop of water on the top one, will flow down and it will hit the second line. And then from that line, I typically will draw a line up, and then I connect these two lines. The line on the opposite face is simply the exact parallel line to the one drawn prior. So let's highlight these lines. So you have these two blue parallel lines. Again, these are the ones where the water would drop from the top line and hit the bottom line. If you draw it such that the water would not hit the bottom line, your chair is going to look a little odd. And now we have these two red lines that again are parallel, and the yellow lines that are also parallel. So it's three sets of parallel lines. That's really the best way to think about these chair conformations. In the convention of the chair, these lines in the up here are closer to you than the lines in the back. So that is considered to be the front of the chair. Now let's put some groups on the chair. You notice in my model that I have these hydrogen atoms all over the chair. The positions going up and down, it alternates. Every other carbon atom goes up, down, up, down, up, down. And you draw them perfectly straight up. And the way to recognize where to put a line up or down is if these two lines are coming together to form kind of an up arrow, you go up from it. In this case, these lines are both kind of going down, so we go straight down. Now, the other lines that we're going to draw kind of around this side, these have special names, we'll talk about them in a moment. These other lines are often a little bit harder to draw, but there's an easy way of remembering what angles to draw, and that is that every single carbon atom is made up of all four different colors of lines as drawn here. So this particular carbon atom has a yellow, a red, and a black, and so it needs a blue. So this one gets this blue. This one already had a blue, red, black, and so it gets a yellow. This one has had a red, yellow, black, and so it gets a blue. These two central positions are the ones that are most frequently misdrawn. But what you again do is draw parallel lines. In this case, they both need red lines. And the key thing is to draw those red lines out of the ring, that is, exiting the ring, instead of putting them into the middle of the ring. It gets very congested if you do it that way. And actually, the angles are wrong too. You'll see if you look at your model kit. So again, we would fill these all, excuse me, we would fill these all in with hydrogen atoms. And in this case, we have this perfect model that matches this model that I'm playing around with here. So let's look down, or look up or down, however you want to say it, one of these angles, one of these bonds. So now we're looking along this red bond here. We would see that this yellow bond to a hydrogen is this yellow bond to the hydrogen, and this blue bond to the hydrogen is this blue is this bond here. We can draw these little squiggly lines to represent that is the rest of the ring. It's often challenging to try to draw the whole ring at once, but you can. It's a nice little challenge. And in looking at this, I want to point out that these particular positions have names. So the positions that are up and down, the ones that I've highlighted as being drawn in circles, those are called axial positions. The way you can remember it is if it's kind of like the Earth on its axes. You can rotate your molecule around on the axes. And similar to the idea of the globe that we can look at, the other positions are called equatorial, so they go around the belt of the molecule. And you can see in this model kit that I've made, I've highlighted that one of these sets of bonds has these pink bonds and the other set of bonds has white bonds. If your model kit doesn't have different colors, you could also attach little pieces of tape if you wanted to try to keep these things straight. So now let's put some substituents or some groups on the rings. So if you have this molecule, like I just made for you here, you can see that there is a black ball here, a red ball, and a blue ball. The red and blue ball are trans to each other, they're in opposite faces. The black and the red ball, you could say, are cis to each other. And so the way we look at this is we draw our chair form, again, where we have the drop of water that could fall off, and we can add some substituents to it. I've highlighted that I'm going to call this bond between the red and blue this bond here. You can actually choose whichever bond you want to make that bond. I think it's easiest often to start on one side or the other. And so the way that we have to look at this is, so this molecule up in the top left, we are looking straight down at it as if we're hovering above it. And so we're going to try to look straight down on this molecule as well. And so we have all these positions. We have axial and equatorial at this red position, and axial and equatorial at the blue position. And so if we look at the first thing that we would encounter on this molecule looking straight down at it, the red is coming out at us. And actually this axial position is coming out of the plane of the board at us. And so we would draw in that this red is this top position, because it's the first thing you'd encounter. And as it turns out, the blue is going away from us on this form here. And so again, the blue would be this bottom axial position here. Now, if we look at the carbon over here, we have to count around the ring, 1, 2, 3, and we can go, in this case, clockwise around the ring. And we find that the black bonded ball is on this third carbon away from the blue. And we would recognize now that, again, the first thing you would encounter if you're looking down at this molecule, the black ball is coming out at us. And the first thing you'd encounter is if you're going down this molecule, or going kind of like a plane, like a cutting cross sections through this molecule, the first thing you would encounter is this black ball here. And again, this hydrogen atom is further away from us. So in order to assess which ring is, or which orientation this ring could exist in, it's important to recognize that this ring actually has a conformational flexibility. It has ring flips, and I'll be showing you, let's look at some ring flips here with a molecule, moving it back and forth. And it's good to practice how to make these molecules move back and forth. When you're drawing the ring flip form, what you can simply do is make sure that you draw another set of parallel lines. In this case, so this time the water is flowing from left to right and falling off. This time you draw it so the water would flow from right to left before it hits the second one and falls off. And this will make sure that you've drawn a correct ring flip form. It's also a good idea to keep track of your carbon atoms. So in this case, I've put a red square around this atom, and this atom down here is the same carbon atom. And again, a model is really helpful in seeing how this works. And so again, looking down at this molecule, the first thing you encounter is the red atom. But now the red atom is no longer axial, it's equatorial. Similarly, the first atom that you encounter if you're looking at this, the carbon that's labeled with 1 is a proton, and then the blue. And now you hit the proton in the axial position and the blue in the equatorial position. And finally, we recognize that the black atom has moved from equatorial to axial. So all of the equatorial have become axial, and all of the axial have become equatorial. That's another way you can check to make sure you have done a ring flip. So the last thing that we're going to look at is a quick assessment of which side is more stable than the other side. So big groups in axial positions are higher in energy. And we can look at why that's the case. So if we look down this bond, this bond highlighted in yellow, we would get this Newman projection shown here. And you can recognize that there is this gauche interaction. Remember that gauche interactions are higher in energy than other interactions. If we looked along the same bond in the ring flip form, we would see that this red ball no longer has a gauche interaction, and instead just has this interaction with these protons highlighted in red and blue. I've drawn these R groups to help you keep track of the rest of the molecule. Feel free to pause the video and make sure that this makes sense to you in terms of how I've drawn these Newman projections. And for those who are watching carefully, you might say, well, what about this bond here, this blue highlighted bond, where you have red and blue gauche interactions? I'll take a brief moment to pause here and point out that I've been using this nomenclature for a while, where these are overlapping. You can think about these as overlapping spheres of influence. These are representing a steric clash when two groups are too close together, and I've highlighted kind of that one is from the red side and one is from the blue side. Well, you can see that there is this gauche interaction when you're sitting when you have two large groups that are equatorial, but when that is less than having all of the gauche interactions when you have both of these groups axial. So again, you can work out how many types of steric clashes would be on each side. So now there's the question that you can go ahead and pause for yourself. Which side is more stable? Is it this left side or is it the right side? And we have to make a big assumption here. We're going to go ahead and make the assumption that the red and blue and black balls are all the same size, because actually the bigger the size, the worse these interactions are. And not all these groups have equal, they don't all have equal sizes, and therefore their steric clashing interactions all have different levels of energy associated with them. Again, the bigger the steric clash, the worse it is. So 3, 2, 1, it is indeed the right side. In this case, you have 2 equatorial and 1 axial, and 2 equatorial and 1 axial is better than 2 axial and 1 equatorial. And again, this is making the assumption that all these groups are the same size. So let's make the assumption that they're all methyl groups, and then that statement is true. Thanks for the slightly longer than usual attention span, and I hope you have a good rest of your day.